Okay, so that was about these entrance lengths, and real quickly, the one applied part, or the important part, is a lot of people then came up with expressions for us to calculate when that happens. So how long is this? And just these. Again, we do notice when we do the experiments that there's just a stark difference between laminar and turbulent flow. So you should expect any equations you have to describe these types of things have to be pretty different. And these are just the equations that help you calculate what an entrance length to a system is. And the system being a reservoir feeding fluid, a pipe. You could actually, there's even expressions as well for other ones, but they all rely on some Reynolds number approximation, which is important for you to calculate. So you have an internal flow system, calculate Reynolds numbers, and then you can get at what these entrance lengths are. That's the diameter of the pipe as well. That's good and great. So these are just things that you can calculate. I mean, that's RE is just something you calculate with a density, the viscosity, the diameter, and the velocity. But they certainly tell you things as well based on like their size, right, the relative size of them, and that's just great, kind of a important thing to have. If I have some sort of system like this, and let's say it's maybe like a really skinny pipe, and this is the length of, let's say, my pipe system that I have to work with. I know for a fact, since there's an entrance point, that there is an entrance length that I need to calculate. So, given some flow rate out of the pipe, well, right, from that process you go, right, I know that this volumetric flow rate is cross-sectional area times the velocity. So, I know this because you can measure gallons per minute, etc. You could just put a little bucket here and fill something up, take a little timer, and then you get a volumetric flow rate. This equation helps you get the velocity. So there's your velocity value. The fluid itself has a density and has a viscosity associated to it as well. And then, of course, you can also calculate diameter of a pipe. Can't stop me from putting some measurement device on there and seeing how the diameter of what this pipe is. So right off the bat, this is the only tricky thing that most people, I guess, you can forget, right? You go like, you get stuck because you're given a flow rate, and then you're going like, but I need a V for my Reynolds number. It's not that bad. You just need to do this calculations as well. So from all that, what you do is you can then calculate Reynolds number. So the water gets some velocity, and this was a function of the flow rate. This is the diameter of the pipe, boom. And then you do your little checks. You say, well, is this less than 2,000? If it's less than 2,000, if you want to calculate that entrance length, it's just going to be that relationship. So it's actually linear, and this is diameter. So really move this over, and that would give you the entrance length. More importantly, is just really the comparison, right? Because if this number is just like much less than the actual length of the pipe, well, that's just that all that says is that for any type of like system we're trying to say, you just don't need to care about the entrance length. I can just say for my whole piping system, it's valid to really draw this little picture where I have fully developed flow throughout the entire piping system. So this entrance length calculations, what they're telling you is, can I really say it's fully developed for most of the regime? Problematically, though, is if it's like, right, I mean, worse is if you had this situation, which you never should really be in. But if the entrance length is bigger than the actual length of the pipe, that means that like there's no fully developed ever. Throughout the entire length of the pipe, you would just know from a Reynolds number calculation that just that. I can't say that the velocity profile is changing. Usually what that means is make your pipe longer, okay? And really you always want this situation. So for any sort of piping system, you really would like the entrance effects to be fairly small. So make this big, making this pipe length enough so that you don't really have to care about this. If that is the case, then we get a lot of expressions that can tell us things about pressure drops. You kind of really need a lot less, because if it's just like less but not that much less, that would mean you would be in a situation, right? That means you are in a situation where it's like developing, still developing, and then like let's say here, now it's fully developed where that velocity profile does not change ever. So that would mean, so this is like LE, and then this whole thing is the length of the pipe. That is problematic because now you have the situation where I know, well, past that, I know there's entrance lengths. I know there's entrance lengths like the first half of the pipe, and then the next half of the pipe, there aren't entrance length effects. So you don't really want to be in that situation. We don't even have tools to handle that if your pipe length isn't long enough to not disregard the entrance lengths. But the only tool you have are those equations that I put down where you're given a pipe system, calculate your Reynolds number, see if it's laminar or turbulent, and then use those equations to actually calculate entrance length and then determine effects based on that. Is it valid for me to say the flow is fully developed is what the entrance length is telling you?